Centrifugal pumps are a subclass of dynamic axisymmetric work-absorbing turbomachinery. Centrifugal pumps are used to transport fluids by the conversion of rotational kinetic energy to the hydrodynamic energy of the fluid flow. The rotational energy typically comes from an engine or electric motor. The fluid enters the pump impeller along or near to the rotating axis and is accelerated by the impeller, flowing radially outward into a diffuser or volute chamber, from where it exits. Common uses include water, sewage, petroleum and petrochemical pumping. The reverse function of the centrifugal pump is a water turbine converting potential energy of water pressure into mechanical rotational energy. History: according to Reti, the first machine that could be characterized as a centrifugal pump was a mud lifting machine which appeared as early as 1475 in a treatise by the Italian Renaissance engineer Francesco di Giorgio Martini. True centrifugal pumps were not developed until the late 17th century, when Denis Papin built one using straight vanes. The curved vane was introduced by British inventor John Appold in 1851. How it works. General explanation: like most pumps, a centrifugal pump converts mechanical energy from a motor to energy of a moving fluid. A portion of the energy goes into kinetic energy of the fluid. Fluid enters axially through eye of the casing, is caught up in the impeller blades, and is whirled tangentially and radially outward until it leaves through all circumferential parts of the impeller into the diffuser part of the casing. The fluid gains both velocity and pressure while passing through the impeller. The donut-shaped diffuser, or scroll, section of the casing decelerates the flow and further increase the pressure. Fluid dynamic principles. Applying classical mechanics theory, assuming viscosity of the liquid equals zero and no energy loss for the work of energy transferring from impeller to the streamlines, which means that all separate flow will be uniforms. The new description: observe a mass going along a straight vane impeller, there are these forces impact on eta, 1 the impeller vane push on it a force Fc, it reflect an anti-force F on the vane, 2 the centrifugal force Fc pull it fly out, dynamic head pressure, applying Bernoulli principle, the first force cause the absolute velocity of the object as circumferential speed, which means dynamic head pressure. Static head pressure, the second force create the static pressure. If a mass moves radially outward along a vane of the impeller, its orbit will be a spiral-shaped curved. We can easily calculate it eta unregistered trademark s angular speed in 2 dimensions. The angular velocity I per mil is given by. So during its movement the centrifugal force Fc always present as the centrifugal acceleration increase linearity on the radius of rotary r, variable, in constant gravitational acceleration g, static pressure of a column of water h is. In the centrifugal acceleration increase linearity from a 1 position to a 2 position, static pressure of a column of water a 2 or 1 is. In the case the discharge of the pump is 0, static pressure save eta unregistered trademark s original value in the outlet of the pump is open air of static pressure created by the impeller drop to 0, static pressure transfer all to the dynamic pressure in vector which is highest value. For example, R1 equals 2 cm equals 0.02 m. R2 equals 8 cm equals 0.08 m. I per mil equals 50.2 I euro. Apply similar calculation, we will have 6 cm column of water present in that area will give the static pressure equals 3 bar, head pressure created by straight vanes impeller. Depend on this logic, the head pressure created by the straight vane impeller is. The head pressure created by the backward curved vane impeller is rotary transfer factor, fraction rotary angular speed of the flow and rotary angular speed of the impeller. Call rotary transfer factor phi per mil equals 1 for the straight vane impeller, phi per mil 1 at variable from 0 to 1 depend on the discharge of the pump. For the backward curved vane impeller, head pressure created by backwards curved vanes impeller. The necessity of the new theory. Compare the two-way, the old and the new description. How the impeller supply energy for the object going through it. We see, new way shows how the centrifugal force appear and it's effective on an object going through the impeller. While the old way only mentioned about the inertial force interaction between the impeller van and the object, which means that conservation of momentum principle cannot ever describe centrifugal force including energy relation with it because it is the diametrically force it cannot make the torque on the rotary shaft. The old description, by Sir Euler in 19th century, conservation of momentum, another consequence of Newtonian unregistered trademark S. Second law of mechanics is the conservation of the angular momentum which is of fundamental significance to all turbomachines. Accordingly, the change of the angular momentum is equal to the sum of the external moments. Angular momentums are, qa, ra, q at inlet and outlet, and external torque m and friction moments due to shear stresses m acting on an impeller or a diffuser. Since no pressure forces are created on cylindrical surfaces in the circumferential direction, it is possible to write EC as, IQ equals m plus me, Euler's pump equation. Based on EC 1.13 Sir Euler developed the head pressure equation created by the impeller see Fig. 2.2. In EC, the sum of four front element number call static pressure, the sum of last two element number call velocity pressure. Look carefully on the Fig 2.2 and the detail equation. It is so harder to study and understand it. Especially and very strange that the curved respond of this equation is always linearity. HT theory head pressure A. G equals between 9.78 and 9.82 meters per second 2 depending on latitude, conventional standard value of exactly 9.80665 meters per second 2 barocentric gravitational acceleration, U2 equals R2 I per mil the peripheral circumferential velocity vector, U1 equals A1 I per mil the inlet circumferential velocity vector, I per mil equals 2 I euro n angular velocity, W1 inlet relative velocity vector, W2 outlet relative velocity vector, C1 inlet absolute velocity vector, C2 outlet absolute velocity vector, triangle velocity, the color triangle. Formed by velocity vector U, C, W called triangle velocity. This is an important role in old academic. This rule was helpful to detail EC 1, become EC 2, and wide explained how the pump works. Fig 2.3 shows triangle velocity of forward curved vanes impeller. Fig 2.3 shows triangle velocity of radial straight vanes impeller. It's illustrate rather clearly energy add to the flow inversely change upon flow rate Q, efficiency factor, where, is the mechanics input power required, is the fluid density, is the standard acceleration of gravity, is the energy head added to the flow, is the flow rate, is the efficiency of the pump plant as a decimal, the head added by the pump is a sum of the static lift, the head loss due to friction and any losses due to valves or pipe bends all expressed in meters of fluid. Power is more commonly expressed as kilowatts or horsepower. The value for the pump efficiency may be stated for the pump itself or as a combined efficiency of the pump and motor system. Vertical centrifugal pumps. Vertical centrifugal pumps are also referred to as cantilever pumps. They utilize a unique shaft and bearing support configuration that allows the volute to hang in the sump while the bearings are outside the sump. This style of pump uses no stuffing box to seal the shaft but instead utilizes a throttle bushing. A common application for this style of pump is in a parts washer. Froth pumps, in the mineral industry, or in the extraction of oil sand. Froth is generated to separate the rich minerals or bitumen from the sand and clays. Froth contains air that tends to block conventional pumps and cause loss of prime. Over history, industry has developed different ways to deal with this problem. One approach consists of using vertical pumps with a tank. Another approach is to build special pumps with an impeller capable of breaking the air bubbles. In the pulp and paper industry, holes are drilled in the impeller. Air escapes to the back of the impeller and a special expeller discharges the air back to the suction tank. The impeller may also feature special small vanes between the primary vanes called split vanes or secondary vanes. Some pumps may feature a large eye, an inducer or recirculation of pressurized froth from the pump discharge back to the suction to break the bubbles. Multistage centrifugal pumps. A centrifugal pump containing two or more impellers is called a multistage centrifugal pump. The impellers may be mounted on the same shaft or on different shafts. For higher pressures at the outlet, impellers can be connected in series. For higher flow output, impellers can be connected in parallel. A common application of the multistage centrifugal pump is the boiler-fed water pump. For example, a 350 MW unit would require 2 feed pumps in parallel. Each feed pump is a multistage centrifugal pump producing 150 liters per second at 21 pa. All energy transferred to the fluid is derived from the mechanical energy driving the impeller. This can be measured at isentropic compression, resulting in a slight temperature increase. Energy usage. The energy usage in a pumping installation is determined by the flow required, the height lifted and the length and friction characteristics of the pipeline. The power required to drive a pump is defined simply using SI units by where is the input power required, is the fluid density, is the standard acceleration of gravity, is the energy head added to the flow, is the flow rate, is the efficiency of the pump plant as a decimal, the head added by the pump is a sum of the static lift, the head loss due to friction and any losses due to valves or pipe bends, all expressed in meters of fluid. Power is more commonly expressed as kilowatts or horsepower. The value for the pump efficiency may be stated for the pump itself or as a combined efficiency of the pump and motor system. The energy usage is determined by multiplying the power requirement by the length of time the pump is operating. Problems of centrifugal pumps. These are some difficulties faced in centrifugal pumps. Cavitation. The net positive suction head of the system is too low for the selected pump, whereof the impeller can be worsened by suspended solids, corrosion inside the pump caused by the fluid properties, overheating due to low flow, leakage along rotating shaft, lack of premier. Centrifugal pumps must be filled in order to operate. Surge. Centrifugal pumps for solids control. An oil-field solids control system needs many centrifugal pumps to sit on or in mud tanks. The types of centrifugal pumps used are sand pumps, submersible slurry pumps, shear pumps, and charging pumps. They are defined for their different functions, but their working principle is the same. Magnetically coupled pumps. Magnetically coupled pumps, or magnetic drive pumps, vary from the traditional pumping style, as the motor is coupled to the pump by magnetic means rather than by a direct mechanical shaft. The pump works via a drive magnet, driving the pump rotor, which is magnetically coupled to the primary shaft driven by the motor. They are often used where leakage of the fluid pumped poses a great risk. They have no direct connection between the motor shaft and the impeller, so no gland is needed. There is no risk of leakage, unless the casing is broken. Since the pump shaft is not supported by bearings outside the pump's housing, support inside the pump is provided by bushings. The materials of construction of these bushings and the required clearances of the parts may restrict the kinds of fluids for which this kind of pump may be used. Advantages: there are no drive seals, therefore the risk of leaks is completely eradicated. This means that hazardous liquids can be pumped without spillages. Less heat transferred from the motor or the pump chamber is separated from the motor by an air gap. This provides a thermal barrier. Complete separation of the liquid means that liquid cannot seep into the motor from the pump. Reduced friction. Magnetic coupling can be broken if the load of the pump is too great. By the magnetic coupling breaking, it means the pump does not overload and get damaged. Eliminating the drive seals gets rid of leaks, friction loss, wear and noise. It provides complete separation of fluid from the pump drive, and nearly 100% transfer of motor power into pumping power. Disadvantages: liquids containing ferrous particles are problematic when a magnetic drive pump is used. This is due to the particles collecting on the impeller magnet, and over time causing the pump to stop working. Some energy is lost in the coupling. This is primarily due to some magnetic resistance. If unexpectedly heavy loads occur, it may cause the coupling to slip. Principle of operation: the impeller of such a pump is magnetically coupled with the motor, across a separation wall which is resistant to the fluid pumped. The motor drives a rotor carrying one or several pairs of permanent magnets, and these drag around a second pair, S, of permanent magnets attached to the pump impeller. Priming: most centrifugal pumps are not self-priming. In other words, The pump casing must be filled with liquid before the pump is started, or the pump will not be able to function. If the pump casing becomes filled with vapors or gases, the pump impeller becomes gas-bound and incapable of pumping. To ensure that a centrifugal pump remains primed and does not become gas-bound, most centrifugal pumps are located below the level of the source from which the pump is to take its suction. The same effect can be gained by supplying liquid to the pump suction under pressure supplied by another pump placed in the suction line. See also, axial flow pump, effects of Mach number and shock losses in turbomachines, net positive suction head, pump, seal, specific speed, thermodynamic pump testing, turbine, turbo pump, references. 7. Fluid Mechanics by Frank M. White, PG 696, 6e.